Ladies and gentlemen, welcome to this month's webinar. At least for me, I know I send out a lot of webinars each month. So today we're going to talk about where does the bell curve come from, and see a few familiar names / faces in the attendee list. So some of this will be a bit of revision, but some of you might have joined just to understand where the bell curve comes from. And so before we start talking about what the bell curve is and where it comes from, I understand that some of you might have heard of it, some of you might not have, some of you might understand there's a bit of meaning behind it, some of you might think it's just a pretty shape. Let's look at what it is we're trying to understand when it comes to things that we use the bell curve for. You can see on the screen right now, one of the most important components or machines or products or whatever you want to call it that we have ever come up with, the ball bearing. Fantastic device for supporting a rotating shaft while minimizing the friction when that support is provided. And because of that, ball bearings are almost ubiquitous in the overwhelming majority of mechanical machines we have. Now, with ball bearings, we are interested in understanding how long it is going to take before it fails. Problem with that is that failure is a random process. Because failure is a random process, seemingly identical bearings will fail at different times. Now, at this point of some of my courses and webinars, I get into a very philosophical debate with a hobby physicist in the panel who says, you know, none of those ball bearings are identical. One has a defect here, one will have a service crack there, and so on and so forth. And that person is 100% right. There is no such thing as two ball bearings with every atom molecule arranged in exactly the same way. But one of the more useful interpretations of identical is when it applies to two or more things, is that something can be considered identical if it is indistinguishable. And while there might be differences in each ball bearing's microstructure, unless we can see them, each ball bearing is treated identically by us because there is nothing we can do to differentiate them. So for all intents and purposes, until we examine these ball bearings in greater detail, they are identical. We will treat them identically. So if we were to test or observe how long it took for a number of these ball bearings to fail, we know that there would be significant variation. Now, for those veterans of my webinars, you'll be familiar with the random hand of failure. For those who are not, I use this illustration to represent all the different factors that drive, in this case, how long it takes for a particular ball bearing to fail. In fact, we know what these factors are with a fair amount of certainty. The most significant factor when it comes to ball bearing failure is particle contamination, kind of the big deal. And you can see that after that, it's misalignment, disassembly damage when you take it apart, put it back together, and then insufficient lubrication, then too much humidity, then manufacturing defects, and then excessive loads. So if you want to make your ball bearings last for a long time, you need to look after them. But suffice to say, these are all factors which will introduce uncertainty to how long it's going to take for our ball bearing to fail. Now, when it comes to time it takes for our ball bearing to fail, we are not measuring time in terms of calendar time. No, for ball bearings, we measure the age of a ball bearing in terms of cycles or revolutions. But it's convention for time to failure to be used in the world of reliability engineering to essentially describe how old something is. And it depends on how your product ages before you can work out how or what metric you should use to assess how old something is. So, but for ball bearings, at least, we use cycles. Now, you can see here a number of blue dots dropping from the random hand of failure. And each one of these dots represents how long it took for one ball bearing to fail. And you can see the horizontal axis represents time to failure. So the ball bearings, the blue dots on the right represented ball bearings that lasted a lot longer. The blue dots on the left represented ball bearings that didn't take very long to fail at all. Now, this is something that our primitive human brain does not like. What do we mean by that? We would much prefer if we knew exactly when each ball bearing was going to fail. This is going to be so much easier for our primitive human brains to comprehend, and even better than that, it allows us to schedule things. We're able, if we know precisely when each ball bearing is going to fail, we're able to essentially swap them all out the day before. We can put that exchange date in our calendar. We can plan for it. We can tell the ball bearing replacement team to be on site on Thursday, the 4th of May, etc., etc. This is how we prefer to run our lives. But in practice, failure is a random process. But just because something is random doesn't mean it's unpredictable. You can see straight away that from these data points, there's a region where it appears as if these are blue balls are occurring with higher density. So this means that our ball bearings are more likely to fail here. Now, this is one pattern or one characteristic we can pretty easily identify. It's not a strong characteristic per se. We can't really say anything too much beyond that, but you can see that there is at least some way we can characterize how this ball bearing fails. So it's just because something is random doesn't mean it's not predictable. But getting the words out of my mouth. It isn't easy to see the density with these data points. So there are lots of other visualization methodologies out there that can really help us. One of the more common ones is the histogram. And histograms use bars to represent data frequency or the approximate likelihood of data. Essentially, what we do is we break our prospective time to failure into what we call bins. And we count how many data points fall into a particular bin. And on top of that bin, we draw a bar which represents how many data points have fallen in the bin. So the bin occurs at the base of a histogram bar. And conventionally, we like to keep those histogram bars the same width to help sort of normalize or sort of calibrate how we visualize density. So here is one way we can better characterize the random process of our ball bearing failing. You can see that this histogram does indeed seem to show a better, or does a better job, I should say, of characterizing the uncertainty in failure. But it's not super smooth yet. So even though it's not super smooth, we can still see there's some there is some trends at play. But suffice to say, you can't use this histogram to comfortably work out or provide information for decisions like how often should I service, when should I replace ball bearings, so on and so forth. So we can improve our visualization by getting more information. When I say that, I mean lots more information. And let's just say we were to test 1,000 ball bearings and get their times to failure. Well, you can see the histogram we now have is a lot smoother with a much clearer pattern. And that's starting to give us some really good understanding of how our ball bearing is failing. And we could keep going. If we had an incredible amount of data, our histogram would eventually turn into this shape here. Let's call this the ultimate histogram shape. The bars are now so small that there appears to be no jagged edges at the top. It just collapses to a perfectly smooth curve. Well, to be fair, this is called the probability density function or the probability density curve. So the top of this orange shape is described by this thing we call the PDF. And the PDF gives the relative probability that a continuous random variable is equal to a specific value. Very textbooky term. And you can see that we have another way of representing the PDF where we have this f of t, function f of t, which helps us answer the question, when will it fail? You can see that Carl has asked a question, why is bell curves trading analysis better than other systems? I need some more context for that one. I might be showing an embarrassing lack of lack of knowledge here, but I'm not entirely sure where bell curve trading comes from. So Carl, if you want to expand upon that, that'd be fantastic. But the PDF curve itself, of which bell curve is one, is very useful for helping us understand or characterize random variables. So the PDF or probability density function helps us visualize the values random variables are likely to have. The higher the curve, the more likely it is for a random variable to have a value around that place. So for example, if we drop 100 data points, you can see these 100 data points are going to fall on our horizontal axis, density that is driven by that PDF curve above. And the shape can tell us a lot about how our system fails. So this is going to be revisions for some people, going to be brand new information for others. If we see a bell curve which has a peak, it looks like it's a mountain. It has a local maxima. If you see this is not a bell curve per se, but a PDF curve which has a little peak, then without you having to do any root cause analysis, you know straight away that your system is wearing out. In this case, our ball bearing is wearing out. That's just how statistics work for wear out failure mechanisms. A wear out failure mechanism is one that accumulates damage. So every single day your device is being used, it accumulates more damage. And the next day, as a result of that damage being accumulated, it is weaker for it. And so when we accumulate damage, every day a surviving system is still somehow managing to work, it is less likely to get through that day. Statistically, that's what wear out looks like. You'll have a PDF curve, which when that PDF curve of time to failure is plotted, will have a peak, a mountain, a hill, whatever you want to call it. Okay, so Carl's asking, what are the limitations of a bell curve? I'll have to get back to that one later on because much of the webinar is dedicated to answering that question about the bell curve. Now, we have, for this PDF here, you can see that even though our data stops roughly there, in fact, that little circles are not calibrated, that little circle is supposed to go around the maximum or the blue data point, which occurs with the highest time to failure. Many PDF curves extend indefinitely, even if you can't see it. So this PDF curve actually does as well. But the problem with, well, not the problem, but this PDF curve, when it extends all the way to an infinite time to failure, the height of that PDF curve is so infinitesimally small that the probability of an extraordinarily large time to failure for all ball bearing is inconceivably small. It's not zero, so it's still plausible for our ball bearings to last an extraordinarily long period of time. However, even though it's plausible, the probability of occurring is incredibly small, and we tend to see data limited to the points of our PDF curve that we can easily see above the axis. So that, in a nutshell, is a summary of the PDF curve. Now, this whole webinar is all about this thing we call the bell curve. And the bell curve is a particular type of PDF curve, and you can see it on the screen now. And it's called the bell curve because it looks a bit like a bell. Now, when I was introduced to statistics in high school and everything else, I was simply told about the bell curve, and it was assumed that it was some nice curve that some dude or dudette drew that was found to be relatively good on to model uncertainty and randomness generally. What I didn't realize is that the bell curve is not just a shape, an empirical shape. It is actually a shape based on a very important underlying physical phenomena. So there is a reason, and because of that, there is a reason we see this bell shape in the world around us. So all I'm going to do right now is I'm going to take you through a visual journey of where the bell curve comes from. And I'm going to start with inventing an absurd random variable. We'll call this random variable X, with an absurd probability density function. When I say an absurd probability density function, I mean a PDF that hopefully you will agree has no place in the natural world. You can see there's a square and a triangle. And yes, this is the square and the triangle combined to create a single PDF curve. The mean of this PDF curve is at the junction between the square and the triangle. But this PDF curve is created by me to represent completely unnatural random variable. Now, the random variable could be, for example, the weight of a rhinoceros, or the height of a human being you randomly select, or how much rain you're going to experience in a particular day. Notwithstanding, the absurd PDF makes all of those example random variables redundant, but it's trying to paint the picture of a random variable which has a very unnatural variation associated with the values it generates. So let's start with an absurd random variable, and this random variable will have a value which is governed, whose density is governed by this absurd PDF. And so it's more likely to have a value which is clustered around the peak of that triangle. But the reason why I'm doing this is because I want to examine what happens when we add two random variables together. In this case, I want to add one random variable that's described by that absurd PDF, and I want to add it to another random variable which is also described by that same PDF. Now, it won't be the same, it won't have the same value. The reason being because it's a random variable. So let's just say, for example, if I was adding the weight of two rhinoceros together, I would go weigh rhinoceros number one, which is random variable, say R. Then I go weigh the weight of rhinoceros 2, random variable R2. I'm going to add those two random variables together. Now, those random variables are the same in that they just are from the same process, i.e. how heavy a rhinoceros becomes. And then I'll get another random variable, which is a sum of those two. Now, if I was to add the weight of two rhinoceros together, then that new random variable, sum of those two weights, is going to be described by its own unique PDF curve. Now, when I add X and X together in this case, the PDF curve, which describes the sum of those two random variables, looks like this. Now, bet that was not what you're expecting. It is clearly not a square and a triangle anymore. You can sort of see the square and the triangle sort of exist in there, but already you can start seeing that when we add two random variables together, you start to smooth out the PDF curve, which is a very natural characteristic of this process. I can see that Carl's asking a few questions. I'm going to get to some of them as we go. One of the most recent questions Carl asked is, are there any thoughts on the skew in the bell curve? Now, a bell curve has no skew by definition. When we say skew, we're talking about a skew to the left or skew to the right, where it has essentially looks like the bell curve's been pushed. And the PDF curve I showed you at the start of this lesson had a skew, but that was not the bell curve. The bell curve was the one I showed you at the very end. And when we at the very end of that introduction, and we're going to focus on the shape very shortly. So let's go back to the scenario where I've added two absurd random variables together. Look what happens to this PDF curve when I add a third random variable, a fourth random variable. The PDF curve shape changes as I keep adding more and more random variables together. So now we have this PDF curve describes 7 random variables added, 8 random variables added together, 9 random variables added together, 10 random variables added together. You can see quite clearly we have that quintessential bell shape in our PDF. So what you're seeing is how the bell curve automatically emerges from any process where we add lots of random variables together. So let's do this example again, but this time I'm going to start with an even more absurd PDF. This absurd PDF is so against what happens in the natural world. It's actually, this PDF curve suggests the random variables are less likely to have a value in the middle of that PDF curve and are more likely to have a value the extreme edges of this PDF curve on the left and right hand side. In a way, it's the opposite of what a bell curve implies. A bell curve implies that random variables are more likely to exist around some central value, and then and the likelihood of those values being true after that become less and less as you move away from that central value. What I'm going to do is I'm going to add the random variable that is generated by this PDF curve up to 30 times. So we're going to do exactly the same thing in a single animation where it gets all added together up to 30 times. And watch what happens to the PDF curve that models the sum of an increasing number of these random variables. You can see very quickly a bell shape is starting to emerge. And now up to 22 times, 24 times, 25 times. As you can see, once we get to 30 times, it is that quintessential bell shape emerges. Now, as a rule, statisticians say that if you add a random variable to itself 30 times, you can all but guarantee this bell curve will model the outcome of that process. And you can see that's a pretty good rule of thumb, because we started with a truly absurd random variable for this little simulation. We have to use computers to generate this PDF curve when we add random variables together. That initial PDF curve, that single random variable, was the opposite of a bell curve. It implied it's less likely for values to be in the middle, more likely for them to be the extreme edges of the PDF curve. And when we added that ridiculous random variable to itself 30 times, the PDF curve eventually emerges. And in many cases, you don't need to add random variables 30 times for that bell curve to start dominating the description of the outcome of that process. Now, this is why we see the bell curve in the natural world around us, because everything is in many ways the product of, not the product, I should say, the aggregate of lots of random processes. We know the bell curve does a really good job of modeling the variation in human height. And that's because the height of a human being, in a way, can be seen as the effect of diet, plus the effect of genetics, plus the effect of exercise, plus the effect of injuries, plus the effect of local gravity, etc., etc., etc. So if all these processes adding up in a way to essentially spit out how tall we are when we grow up, we see the bell curve do a really good job of explaining that variation. Now, originally, when the bell curve was discovered or created, so to speak, nature created, I should say, but when we first started trying to characterize it, it was done by this guy called Carl Gauss. And he was a pretty smart dude. He did lots of maths and lots of astronomy. And he found that when he was doing his astronomical observations, this bell curve shape did a really good job of modeling the errors he made during those observations. When I talk about errors, we talk about the inaccuracies associated with understanding exactly where your telescope was pointing at any given night, the azimuth, the elevation, bearing, direction, all those things. And he found that bell curve did a really good job of modeling the errors in his observations. And so he discovered this bell curve. He also discovered it was really, really useful for modeling lots of other random processes without really knowing why. It wasn't until late 1800s, I believe. I'm sorry, the name of the Russian mathematician escapes me, but the Russian mathematician was able to prove that this bell curve emerges when you add lots of random variables together. In fact, he gave it a name. So to formalize this, what you just saw, if y is a sum of lots of independent random variables, in this case, multiple instances of random variable X, the Y itself will always tend to be modeled by this bell curve. That Russian dude called it the central limit theorem. Any sum of independently, individually distributed random variables will be approximately normally distributed. So the normal distribution is the bell curve. Now, Carl Gauss, who first came across the bell curve, his name is also associated with it. So when you hear the normal distribution, the Gaussian distribution, the Gaussian, or the bell curve, it's all describing the same thing. Carl asks, how does sample size affect the bell curve? Well, it's a broad question, but I think you're referring to how quickly does a bell curve emerge when you add random variables together? And it depends. As I said, if you're adding 30 random variables together and they're all of about the same mean with the same, roughly the same mean, roughly the same variation, you all but guarantee to see a bell curve emerge after you add 30 of those together. If it's a smaller sample size, the bell curve might not emerge. When I say sample size, if it's a smaller number of random variables you're adding, the bell curve might not emerge as quickly. But that said, if the underlying distributions of each of those independently individual random variables, if those distributions themselves weren't absurd the way I created them, they were even just a little bit like a bell curve themselves, then the bell curve emerges that much faster. So there's no, this is how many samples you need to before the bell curve will emerge. But there are some things at play which will then drive how many things get added up before you can all but guarantee that the bell curve will describe whatever it is you're looking at. So let's think. Any thoughts about the central limit theorem and the relationship to the bell curve? I don't know how to answer that. I thought I answered that pretty thoroughly. I thought the central limit theorem, where you add lots of things together, I showed how when the central limit theorem actually says that you'll get the normal distribution / the bell curve when you add lots of things together. So that's the answer to that question is they are inherently related. So for example, there's a definition of the central limit theorem. Any sum of independently, individually distributed random variables will be approximately normally distributed / will be approximately modeled by the bell curve. What that means is you add more and more and more variables together, the bell curve is going to be more and more obvious because the normal distribution is the bell curve. Now let's think about preventive maintenance. Preventive maintenance is a wonderful form of maintenance because it allows us to fix failures before they occur. That's what it's all about. And as a rule, we know exactly what we do for preventive maintenance. So if it's that time of the month, we're going to go to our machine, we're going to change that gasket, check that oil, calibrate this. We're going to change that lubricants. We're going to do this, that, and the other. And as you can see, you might come up with, say, 6 tasks for your preventive maintenance action, preventive maintenance time, I should say. But the overall time you spend on that preventive maintenance job will be the sum of the times for all these little tasks. That's what preventive maintenance is all about. And so when we have a bunch of repeatable actions where the total PM time is a sum of individual task times, we are now essentially using this, we can now apply the central limit theorem to describe how long it takes for preventive maintenance to be completed. So for example, if you have 6 tasks for preventive maintenance, 6 actions, or what's the quite right word here? I want to make sure I'm going to use a term that is as universally understood as possible. Let's just say these are 6 individual tasks within a single preventive maintenance action or activity. And these individual tasks also tend to have their own small substeps as well. And so these individual tasks tend to be normally distributed or tend to be described by the bell curve because of the central limit theorem. And then we add these tasks together, the central limit theorem becomes more and more prevalent. And so we know that preventive maintenance time is wonderfully modeled by the bell curve. So let's do some boring equation stuff. And the reason I'm doing that is because in the workbook, you will have some equations that I'm going to quickly go through. And all I'm trying to convey here is that these equations exist. I'm not expecting you to remember them, but you might hopefully these visual guides through these equations, through these functions, will just help you understand how you can potentially use the bell curve moving forward. Here are 3 bell curves. They're all exactly the same shape. 2 of them have different means, and 2 of them have the same means, I should say, and 2 of them have the same standard deviations. All bell curves are symmetric, so there's no skew. It just depends how tall and short and fat they are. So you can see the blue and the red curves have different means, but the same standard deviation. The orange and the blue curves have the same mean, but different standard deviations. The orange curve represents a random variable where there's more dispersion, more variance, more uncertainty in the values. Still has the same mean as the blue curve. The blue curve values, or the random variable from the blue curve, will tend to have its values more clustered around the mean. So there are the horrible equations you need to come up with a PDF curve. Main takeaway is you want to use Excel or a similar computer program to be able to do this, to be able to use these PDF curves moving forward. Again, these are in your guidebook. The CDF, cumulative distribution function, for bell curves have this S shape, this sort of S shape that is also symmetric about the mean. And as is the case for all CDFs, they approach 1 or 100%. Now, a deep explanation of what a CDF is outside the scope of this webinar, but suffice to say, if your random variable models time to failure, the CDF simply tells you the likelihood that your thing has failed by a particular point in time. And because your thing is going to fail eventually, CDFs always approach 1. You want to have a worked example of how to use the PDF curve. Let's go back to preventive maintenance. Let's just say you did some data analysis and found that the mean of preventive maintenance for your organization is 46.215 minutes and the standard deviation is 8.315 minutes. What is the probability that preventive maintenance time will be between 40 and 50 minutes? Well, because we know preventive maintenance time is modeled by the bell curve, always is, we can describe or represent the random nature of preventive maintenance with this shape here. We can use this equation, which essentially all it does is work out what the CDF value is at 40, and the CDF value is at 50, and subtract the two, which gives you a number, in this case 44.81%, to correspond with the area under the PDF curve between 40 and 50. And that area, 44.81%, gives you the probability that your preventive maintenance time is going to take between 40 and 50 minutes. Now, if you want to learn more about CDFs and PDFs and things like that, Ascendo has plenty of webinars, including ones I've done, that will take you through what this means. But the area under the PDF curve can be used to give you the probability that random variables will assume a value, in this case, between limits such as 40 and 50. And so this becomes very useful if you need to understand how long it's likely going to take for preventive maintenance to be completed. So the bell curve becomes very useful, not just reliability engineering, or the strict interpretation of reliability engineering, but also maintainability as well, or understanding maintenance. Many people believe that's part of reliability engineering, as I do as well. Reliability function, what does that mean? The reliability function tells you the probability that your product is still working. So if the time to failure for your product is modeled by a bell curve, then the reliability function will start at 1 in this case, and have that sort of reverse S shape as it goes down, because everything will eventually fail. So the reliability function for your normal distribution looks like that, and the equations are in the book. The hazard rate. Now, if you want a god-awful equation, look at that god-awful equation on the left-hand side. But what the hazard rate is essentially tells you how how likely it is, the rate at which things are failing if they're still surviving. Now, the hazard rate for all bell curves increases. What's that mean? It's wearing out. The thing we're modeling is wearing out. So that's the sort of the distribution functions in a nutshell. So I'm going to answer some of Carl's questions right now before I move on. I'll go back. Carl asked, any thoughts about the bell curve relationship between the bell curve and performance management? By that, I believe you're referring to how managers or management frameworks and structures tend to try and force the bell curve to describe human performance. Universities, for example, when they're trying to work out if you've marked appropriately or not, often lecturers will be graded on a bell curve. They'll say, well, based on this, not the lecturers per se, but how the lecturers grade their students. They will have, okay, the mean is this, therefore we'd expect to have this many people below, this far away from the mean score this lecturer gives, and this many people above the mean score, so on and so forth. Now, as a rule, I have not seen a lot of literature which actually confirms that the bell curve is useful for modeling performance in students or humans. But even though it's assumed to be used in many managerial frameworks, I think it stems from the fact that the bell curve has been observed so predominantly throughout natural processes, heights of human beings, astronomical errors, all sorts of things tend to be really well modeled by the bell curve. And the bell curve also beautifully aligns with how our primitive human brains characterize randomness and uncertainty. If we are forced to think about randomness and uncertainty, our brains tend to like thinking about random variables or uncertain processes where there is a central value, which is more likely than others. And as you move away from that central value, the random variable values become less and less relevant, or less and less likely, I should say. So that's why I think we see the bell curve used in modeling human performance or performance management. But in practice, I don't believe I've actually ever seen, I don't think I've ever seen any justification or demonstration that the bell curve is the right one to use. We also point out that one thing I haven't covered as well as I potentially should have is one limitation of the bell curve is that the PDF curves, they extend all the way to negative infinity and positive infinity. So if we go back to these three PDF curves, those bell curves, they, even though you can't see it, the left-hand extreme edges of each bell curve goes all the way to negative infinity and all the way to positive infinity. That's not possible if your bell curve is modeling, for example, preventive maintenance time or time to failure. However, if you have enough data, the bell curve is so close to the real distribution of preventive maintenance time or time to failure, and the probability that the bell curve extends below zero is incredibly small, that it becomes a very, very useful useful model for your random process. So one limitation is that it does extend to negative infinity, which is often impossible for many reliability engineering applications. However, it doesn't mean it's an invalid model. The central limit theorem, it will say that as you add lots and lots of random variables, eventually the bell curve will emerge. So if you imagine, if you add 100 random variables together, although what you get is going to be very, 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 very close to the real bell curve, incredibly close, and any differences between that and the real bell curve, where the real bell curve goes below zero, is negligibly small for many scenarios, especially when it comes to trying to make better decisions. So that's one limitation of the bell curve, and hopefully I've answered your question regarding performance management. Yes, I see the bell curve used a lot, but no, I haven't seen a lot of demonstration of it being appropriate. I've also need to point out that when we model performance, it's usually on a scale of 50 to 100%. As a rule, we don't like scoring people below 50%. That's implied, or that is implied as being below average. So we see a lot of performance scores where you get average to awesome. So from 50 to 100%, and the bell curve would likely extend outside the range of 50 to 100% if you're trying to model it in that way. So again, I'm a little bit skeptical that the bell curve is useful in performance management. However, it is often used, and perhaps there are some useful things that fall out of it. But yeah, I'm yet to see an absolute proof that it does model human performance well. Okay, so let's look at another example. So let's just say we are now going to look at a tire. Now, a tire in this case of the tire we're looking at is going to be the tire of a bulldozer. And let's just say that this tire is going to wear out, which of course it will. It's going to wear out. And let's just say in the environment it's being used, any really sharp rocks, which are essentially going to immediately puncture our tire, have been removed. So the only way this tire fails is when the tread is worn away to the extent there's no tread left and our tire punctures as a result. So we've removed all the sharp rocks, and let's just say that we have historical data from 5 other tires that wore out. Now, in this scenario, we can look at the way tires are damaged and understand something that's quite interesting. What do I mean by that? If you have a tire which has traveled 1,000 kilometers, you would expect it to have lost half as much tread as a tire that's traveled 2,000 kilometers. What that means is essentially the tire is losing roughly the same amount of tread for every kilometer or mile it is driven. And the total amount of tread that is lost is essentially the sum of the tread lost in kilometer number 1 plus the tread lost in kilometer number 2 plus the tread loss in kilometer number 3, so on and so forth. And so because the amount of tread you lose is proportional to the age or life of this tire, we can understand that effectively what's going on here is the amount of tread we lose is adding up. And the random variable, which is the amount of tread you lose during kilometer number 1 or each kilometer, is identically distributed with all other random variables, i.e. we expect to lose the same amount of tread every mile, every kilometer we drive. And so this becomes a beautiful analogy, or not an analogy, a beautiful process from the perspective of the central limit theorem. The central limit theorem describes this process beautifully because it's so focused on damage where things are adding up. Anyway, so let's look at this tire in greater detail. We are going to assume that because the tire tread we lose is adding up over its age, that the bell curve is a very useful life model to use. But we have data from 5 tires that have failed in the past. And because we know it's a wear-out failure mechanism and the tires lose tread at approximately the same rate, so the tread we're losing is adding up, we're going to use a bell curve to try and understand the reliability of our tires. Remember, this is a dozer, so it's being driven in potentially harsh conditions on a mining site. So we're not thinking about bitumen or tarmac or concrete. No, it's every day is a bad day for our dozers. So how do we find a bell curve that's going to model time to failure for our tires? And how can we use these 5 data points to get there? I'm going to describe a technique called matching moments. Now, as is the case for most statistical textbooks, the person who writes that comes up with that idea finds the least useful title for a particular process or activity. And so matching moments Doesn't sound very intuitive. What the hell does matching moments mean? Well, in the world of statistics, a moment is essentially a characteristic of a random variable. And so one characteristic that we use a lot essentially is the hypothetical balance point of our random variables. And the hypothetical balance point is what we call the mean. So in this case, we've got 5 data points. We can find the mean of these 5 data points by simply adding up the duration for each one and dividing it by the total number of points. And we want to make sure that everyone knows that this is a mean for these 5 data points and not the PDF curve, which we haven't found yet. Or this is sample mean. We denote it T bar. So T subscript I is the duration for each tire that has failed and is in our database. And N in this case is the total number of data points or total number of tires. So in this case, here are the numbers. Here's the kilometers driven before these 5 tires failed due to wear out. And so that if we substitute these numbers into our equation at the top, we will simply add them up, divide them by 5, and find that the mean, the sample mean, is 19.94. And the Excel formula you can use to make this simpler is on the screen now and is in your guidebook. Then we use something else, which is essentially, we need to try and find the right bell curve for this data set. We need to think about this thing called moment of inertia. What is that? Well, statisticians stole the concept of the moment of inertia from physicists. Essentially, if you have 2 weights on a lever like this, a teeter-totter or a seesaw, you can see how there's a bigger weight on the right-hand side. That's okay because it's closer to the fulcrum than the weight on the left-hand side. If those weights are further out, even though it's still perfectly balanced, it's harder for that thing to pivot. If you have those weights moved closer to the fulcrum, it's easier to pivot. And so statisticians stole the concept of the moment of inertia. And the moment of inertia is essentially how hard it is to make these weights pivot. And so they used the moment of inertia to come up with what we call the standard deviation, which is a measure of how far these data points are away from the mean or the fulcrum. Now, the equation for the sample standard deviation, this god-awful thing here. And so what we need to do, we've already found T bar, the sample mean. Here are our random variable values that we've observed from our database. And we substitute those in. I'm not going to do that here. I'm going to simply say, please use this Excel equation. And because we are focusing on data points, i.e. a sample, the formula you need to use for Excel is stdev.s. STDEV is short for standard deviation, and S refers to the fact that you are trying to estimate the standard deviation of a sample. When you do this, Excel tells you the standard deviation is about 2.455. So now we have the sample mean and the sample standard deviation. If I was to create a bell curve based on that mean, that standard deviation, this is what it looks like. Now, these are 5 data points, so it's impossible for us to visually verify that this is the perfect bell curve for the data points we've seen. But at least at first glance, it seems plausible. At first glance, I should say, this seems plausible. This seems like a pretty decent bell curve for these 5 data points. And so we're onto something here. What this approach is, like I said, matching moments. A moment is a characteristic of a random variable. And so if you choose to match the sample mean and standard deviation with the mean and standard deviation of a bell curve, then you get a bell curve which is approximately right. The more data points you have, the more accurate your sample mean and sample standard deviation becomes, which means the bell curve becomes more and more closely aligns to true bell curve behind the random process. And of course, not everything is described by a bell curve. So in previous webinars and previous courses, I've taught people how we can not only look at how this tire fails due to wear out, but due to, for example, rock punctures as well. With this stone, where a tire drives over this rock or stone, going to be punctured. It's going to have a very bad day. Just a little bit of advanced conversation here. You can use something like a fault tree like this one in order to combine the effects of failure due to wear out or failure due to puncture. There's an OR gate there, which means that our tire will fail if it wears out or if it's punctured. Now, in previous webinars, I've shown how the exponential distribution is used to model things that have a constant hazard rate. Punctures due to sharp rocks are a classic constant hazard rate failure mechanism. It doesn't matter how old or young your tire is. If it goes across a sharp rock, it's going to fail. But then here's a normal PDF we came up with for our 5 tires that wore out. And if we want to combine these two, we can create this wonderful PDF curve, which combines both wear out and puncture. You can see that this captures beautifully what is going on in the life of our tire. You can see the hazard rate is constant at the start and increases towards the end. So let me have a look at some of these questions which are stockpiling up. Still don't know much about bell curves trading analysis. So I need a bit more context on that question, Carl. Carl then asks about the T distribution and its relationship to the bell curve. Well, the T distribution is named after a guy called Student. That was his, what's the term I'm looking for when someone uses a, not their real name. I was going to say pseudonym, but anyway, so the guy who went by the name Student actually worked with in the Guinness Brewery back in the late 1800s, I believe. And he essentially found that if you were to add up lots of random variables, which were all described by a bell curve, then you can actually use this T distribution to describe the likelihood or the uncertainty you have in the mean of those sum of those random variables. And so the T distribution, without getting into too great a deal, is often used to help us characterize the uncertainty we have in the mean of a random variable, because one of the ways of calculating the mean is to add them all up and then divide them by the total number of data points. And so if we're going to do that, for example, I'll go back to my matching moments example, where we essentially get that balance point. We know that the true mean of the process is not, this failure process is not going to be 19.94 kilometers. We know that 19.94 kilometers is a pretty good guess because that's the sample mean. That's the mean based on these 5 data points. But there will always be some errors in this approximation of the mean, and Student's T distribution helps us understand the errors or the uncertainty we have in our approximation of the mean. So 19.94 kilometers is our best guess, but that estimate will increase if we have more data points. So that's where Student's T distribution comes into play. And of course, a full description of the Student's T distribution is outside the scope of this webinar, but that's at a high level how it relates to the bell curve. Nasri writes, when we check for normality of data and find out it isn't that mean the data is outside of the bell curve? I wouldn't say anything is outside the bell curve. I would describe if you check for normality of data and find that normality is not present, what that means is your data is described by some other distribution, not the normal distribution, and therefore the bell curve doesn't describe how your random variable is distributed. So I wouldn't describe that as being outside of the bell curve. It just means the bell curve is not the right probability distribution for you. That's what happens if your data fails the normality check. Kevin writes, does the bell curve relate to the process of fatigue, which is many times described by a log normal distribution? The log normal distribution is a fantastic distribution to use for fatigue. Now, the reason why, can't go into too much detail because time is of the essence, but the log normal distribution, which sounds very similar to the normal distribution, it models processes that multiply together. So for our tire, where the tire tread wears away and the amount of tread you lose every single kilometer or mile is roughly the same, when it comes to fatigue, as the fatigue crack gets bigger, the amount of stress that is concentrated at the tip, crack tip increases. And therefore, for every cycle of stress, the crack grows incrementally more. Crack gets bigger, it grows faster. And that has been shown to be essentially a multiplicative process. The bigger the crack, the bigger the step increase in the crack growth. The reason why that's modeled by the log normal distribution, and the log normal distribution has normal in it, is because when you multiply things together, you actually add their logarithms. So for example, if you multiply 100 by 1,000, you get 100,000. 100 is 10 squared, 1,000 is 10 to the power of 3. And so the answer, which is 100,000, is 10 to the power of 5. Squared, 2, power of 3, 3, 2 plus 3 equals 5. And so it uses a trick. When you multiply numbers together, their logarithms add up. And so the log normal distribution models, essentially uses the bell curve to model the logarithms or the exponents. And that's why it's used a lot for fatigue, because when things multiply together, the logarithms add up and you get the log normal distribution. So I know it's a pretty short description, but yeah, the normal distribution is in the heart of the log normal distribution. The way it's applied is that it applies to random variables that multiply together, which is why it's used for fatigue. Hopefully that's come close to answering your question. Someone writes, the T distribution was so revolutionary for manufacturing beer that it was treated as a trade secret. That's true. Yeah, and that's his name. Yes, S. Gossett. It was often the case that when organizations like Guinness, and statistics was in its, in many cases, in its infancy, while these companies were going through the Industrial Revolution and trying to maximize their outputs and learning about mass production, that many of the employees of these companies were coming up with really important contributions to the world of statistics, including a guy who was working in Guinness Brewery at the time. And it was so revolutionary, it was treated as a trade secret, but he published it under a pseudonym, so the competitors to Guinness wouldn't know that this would be a really cool way of understanding the variation. I think it was in barley grain diameters or something like that. Anyway, so that's the story behind our friend Gossett, who picked the name student for whatever reason when he published the paper. No worries, thanks. Hopefully that looks like I answered your question, Kevin, though. Thank you for the feedback. My answer was within the right ballpark. Thanks for that feedback, Carl. Much appreciated. And in regards to your questions regarding the thoughts of the advantages and disadvantages of the bell curve, again, I don't think there's an advantage or disadvantage per se. It's all about the advantage and disadvantage of how we apply the bell curve. I mean, if we use the bell curve to describe something that isn't based on the central limit theorem, then that's on us. The bell curve is awesome. It's fantastic. It does a great job of modeling random variables where they are all added together. If we choose to use a bell curve for a different scenario, that's on us. So I wouldn't call it an advantage or a disadvantage. I'd just call the things we talked about today characteristics. If you want to use the wrong model, Fred's most favorite example of using the wrong model is to use the constant hazard rate to model everything from satellite failure through to manufacturing defects and infant mortality. That's, again, is on us. So the bell curve is brilliant at modeling things that are based on lots of other things adding up. And I still haven't got to the bottom of bell curves trading analysis yet, but if I find out what it is, I can maybe answer that question. Yes, the bell curve is what it is. Well said, William. Any more questions or comments on where the bell curve comes from before we wrap it up for today? Show of hands, if you guys are brave enough, who thought that the bell curve was just a shape and didn't know there was some sort of underlying theory behind its shape. Be interesting to see how many people just thought that. So I've got one. Dare say there's a few more than that. Maybe we're rushing to find those hands being raised, or maybe some of us, a lot of us genuinely did know there is an underlying principle or theory behind the bell curve. There's another one. Yeah, I'll tell you what, it took me a while before I discovered that there was some theory behind the bell curve. It wasn't just a pretty shape that some person drew because it seemed to describe what was going on, and the equation just seemed like an arbitrarily simple one, so to speak. But no, it was used for several hundred years before a smart Russian dude worked out, hey, hang on, this is why we see this bell curve. When we add lots of things together, whatever the thing we model, or when we model the sum of lots of random variables, the bell curve will almost certainly very quickly emerge. It'll emerge faster if those underlying random variables are themselves described by bell curves or things that look like bell curves. And if you add more random variables together, the bell curve is going to emerge that much faster. Any more questions? Thank you, Evan. Much appreciated. All right, team, as per usual, you've got the workbook, you've got my contact details, you've got Fred's contact details, you've got all the other contact details of our colleagues in Ascendo. Thank you, Patricia. If you have any questions, you know how to reach us. Hopefully you can use the bell curve for good moving forward. Next webinar I'll be doing is on supportability, which is a complete change of pace. And yes, supportability has a very defense or military theme, because supportability seems to be most stringently defined by militaries. But in practice, everyone who's involved in designing or maintaining something is all about supportability. Unfortunately, supportability is often left to the last moment to somehow be baked into our systems. By then it's too late. So next month, I should say, I'm going to talk about supportability, how it relates to reliability. It's obviously kind of a big deal because supportability involves fixing things that break. So if you're in any way, shape or form interested about that conversation, I'll see you the same time in April. And yeah, otherwise looking forward to having that conversation. Thank you for your feedback, Nasri, Jingsong, Michael. You do miss the music of Franz Danzig. Okay, I'm sure that's I'll have to push your request off to the producer / Fred Schenkelberg. If that can help. Thank you, Long Chun. So Fred, I think we're good for today.